Can you hear me? So I'm glad that you are all here today with us to present for you the recommender model for ranking matching houses. I hope you have some energy left for us because it's 5:45. So, yeah. My name is Dania. I'm a data science recent graduate from Bologna Business School. And previously, I was working as data analyst. And I have with me
And
Chiara.
I am Chiara, and I recently graduated in statistical science, and now I'm working from 6 months at the engineering company in Padua.
Yeah, and we both worked on this model during our internship at engineering. So, as you know, like nowadays, like world is full of information that like a vast amount of information is being generated every second. And once you are browsing the internet, you can see like a lot of information when you are searching for simple stuff. So you will be, and all the brands, all the companies want to grab your attention, so they will load you with a lot of information. And you will end up like this poor guy, and you will say like, this is too much information for me. I just want the customized information that is based on my preference when I'm searching for simple stuff. So this was our case for real estate. So in our case, I'll just give you a brief and a simple introduction of what is recommendation system in case you don't have any idea about this. So the simplest definition of recommending system is a subclass information filtering system, which is seeking to predict the rating and preference of a customer would give to an item. And this was one of the main phases for our model. And the second phase was how to have a ranking mechanism for our model. So what was the business goal behind this project? So the main goal was to create an efficient and accurate engine that is matching real estate for the customer portfolio based on their references. And so the system should have like data of real estate that is taking the customer request of what kind of houses they are searching for. Then we will give them back best matching houses based on their preferences and their profile, of course. So here you can see the general workflow of the model that we have implemented, starting from the customer is inputting a new query for their preferences to a happy customer, not like the poor guy that we saw in the beginning. So as I have said, like the model was based on two main phases. So the first thing was to build a recommendation. And this was done by implementing two models, which are the GLRM and deep learning with AUTOENCODER, which I will go in deep in the next few slides. And then we have the ranking mechanism, which is like after having a complete data set of the houses, we need to have a ranking mechanism to give back to the customer best matching houses for their preferences. For today's presentation, we have used American Housing Survey for a purpose to show you a demo. So we have an open source, and it's a national public file that every record is associated with the housing, with the household profile. So it's like it has all the features of the house with the householder profile that we have. The methodology and tools that we have used, so in the first phase was to build the recommendation, as I have mentioned before. And this, the inferring of NA for this phase, the main goal was to create, to inferring the features that was not selected by the user. For this purpose, we have used, as I said, like two models, generalized low ranking model and deep learning with autoencoder to inferring the house features based on the available data that we had in the history. We implemented these two models with the H2O package. And the main idea behind implementing it with H2O, besides it's an open source software, it has a large range of advanced machine learning algorithms that you can like implement. So you will have, while you are working with different models, you will have a constant of one package that you can build all your different models from. And as well that H2O is a framework that enable you to work with big data framework, and it has its own internal data structures that you can play around with, and it's efficient and like it has an optimal efficiency because it's done with the fine-grained parallelism, as well as it's allowing you to serialize your work based on node or cluster or combined both together. So for this model, the generalized low rank model, as you can see, it's approximating the data set based on the product of two low dimensional factors. And it's taking the most important combination of the features and then recomputing for you the original data set based on the features that was available. And the main characteristic of this model, it was enabling us to deal with the categorical variables because like our data set was heterogeneous and it has a lot of different data types that we need to deal with. So this was one of the main idea to implement the GLRM to impute the NA. Here you can see the code which was implemented with H2O. As you can see, it's straightforward, it's easy to implement, so you will just import your package as if you are doing with any other packages. Then you will initiate your H2O service, because as I said, like H2O will enable you to have parallelized computing, so you can give it like the number of nodes that you want for your server. And then you can, for this one, as I said, like H2O has internal data structure. So when you are working with H2O, you need to convert your data set into an H2O data frame. So here you can see, like, you will just give it like H2O frame, so it will convert it to an H2O data frame, and it's basically like Panda's data frame. It's easy to play around with. And then we have to implement the model. And again, like here, H2O is giving you a lot of a set of wide range of parameters that you can tune, you can play around with to understand how your model is working. And you can give it a lot of parameters, and even you can play around with the hyperparameters that you can choose. Then you will just train the model based on the models that you implemented. Then you will predict it, and then you have to convert it back if you want to. If you are more confident with pandas, you can convert it back as data frame of Panda, then you can do more, like to explore more your predicted data. The next model that we used was deep learning with AUTOENCODER, and the main reason of implementing this model was it's giving us more generalized and scalable solution. And what is deep learning is it's unsupervised learning based on multi-layer feed-forward neural network, and it's taking the most important pattern, it's learning the most important pattern of the data and recomputing for you the original database based. So first of all, when it takes the input of your data set, it will convert it to a hidden layer. Then in this hidden layer, you have backpropagation, which is giving a small loss function that it will allow you to, it will make sure that when it's reconstructing your data, it will give you a most similar to your original database. So as I said, like one of the main characteristic was it's giving us a generalized and scalable solution. Here you can see the codes, and as I said, like again, it was with H2O. It's pretty straightforward. It's the same steps. You will just have to play around with with the parameters based on the problem that you have, and you have a wide range of parameters that you can choose from the H2O. Then the next phase now, like we created a history of our data set, which is completed because one of the main parameter of recommender system is one of the fundamental one is to have a completed history of user preference. So after that, we will not give all this history to present it to the customer. We need to have a mechanism to rank the houses that we have to the customer based on their preference. And that's why we have the second phase of the project, which is like scoring. We presented a new scoring formula. And the goal of this one is just, as I said, like to create a ranking mechanism to give us back the houses from most similar to least similar based on the features that was selected by the user. And this formula was inspired by Lucine's score formula, and we customize it based on our data set, and we give it variable importance, which is like custom variable importance. So let's say, for example, we have total bathroom and total bedroom were more important than, let's say, fireplace or porch in this case. And as well as the score was weighting more the houses which was totally matching the customer preferences. So now enough with the boring theory. Chiara will present for you the result, and will show you a practical demo.
Thanks. So during our work, we also have carried out a very lightweight application implemented in FLASK. What is FLASK? How many of you have ever implemented an application in FLASK? Okay, not so much. So I can introduce a little bit of FLASK. So FLASK is a web framework for Python that gives you the tools, the library, and the technology to implement a web application. It's a micro framework. This is really simple and lightweight, but support also extension to add functionality to the application, like, for example, form validation or database uploading, and so on. Moreover, it's really simple because it has only two dependencies, the Workzeug and Jinja. Workzeug is an utility library that permits the web server to connect with the web application. Instead, Jinja is a template language that permits to have a really dynamic HTML pages, so to have request and response and so on. And really important is that FLASK is really easy to learn and simple to use. Now I will proceed with an example. Is an excerpt of our application final that I will show you later. And the basic points of the FLASK application after obviously starting it and setting the variable of the environment are the root. What are the root? These roots are different URLs that the application implements. And these roots are technically saying to the application which URL trigger a particular function. In this case, I will not go in detail in the codes. I will only show some interesting stuff. There are, for example, the render template. You can implement the FLASK with an HTML page, and the request form. So from a previous page, you can request some data that were inserted by the user. On the left, we have put some example code to run the FLASK application on your local PC, so to test it, to see if it's working, and so on. Now, let's go to the results of our project. First of all, the validation of the model. So this plot is showing the percentage of error with the increasing of the missing value inside a query. So, because for tuning the model, we are saying that we are imputing some missing values inside a query. So, how can we say, okay, this model is okay, this model is not? So, we remove some random features from a random query, and we impute it with GLRM or deep learning with some parameters. And we compare these two. So we compare the predicted query with the previous one, the original one, with the features original. In this case, we are showing the GLRM with 10 dimension and 15 dimension, and that is the pink line. And for the deep learning, we choose 250 nodes for the hidden layer, and 150 and 200 nodes for the hidden layer. As you can see, the blue line is always lower than the pink line, so meaning that the deep learning has a lower error than GLRM. In particular, has about 10% lower error than GLRM. Another thing to notice is that I think is reasonably reason. We have with the increasing of the missing value inside a query, the error is increasing because we have less information about what the user wants, and so we can't really be precise in our inferring. Last thing to notice about this plot is about the performance of the GLRM at the beginning. The performance of the GLRM is similar to the one of the deep learning with autoencoder, but only at the beginning when we have like more information and few missing value. Before proceeding with the final application, there is an example. No, sorry, I forgot. Okay, we already said that deep learning without encoder performs better. It has a lower error of 10%, but GLRM is faster. That is because deep learning without encoder need more time to process, is more complex, and so on. This table is showing the time in seconds needed for a complete run of the engine, meaning that we, from the imputing of the missing values to the ranking of the houses. So in this case, we are showing only from 40% of missing value on, and we can see that the GLRM has always a smaller time. And the GLRM practically takes from 30% to half the time of the deep learning without encoder. Another interesting thing is that with the increasing of the missing value, the time is decreasing, meaning that we have less information to process, so it's taking less time. Now, a first example, only to show you from also like a visual point of view, like the different way of inferring for the deep learning and the GLRM. So let's imagine that there is this user that wants this kind of features. So 1 bathroom, 4 or more bedroom, and so on. Now let's see how the deep learning and the GLRM are inferring the other features. Always keep in mind that we are only showing like some feature, an excerpt, but there are also a lot of other features that can be inferred differently between GLRM and deep learning without encoder. So these are the results. We added only to show like air conditioning, fireplace, and total room. For what concerns air conditioning and fireplace, there are no difference between the training of GLRM and deep learning without encoder. But what happens in total room? In total room, there is a difference. Like only for a reasoning point of view, not really like statistical model or mathematical model, you can see that the user wants 4 bedrooms, a separate dining room. You have a kitchen and 2 or more living rooms. How much is the total? 8. So from this point of view, like you can see that deep learning without encoder is predicting better. Now, let's see the ranking of the houses. Keep in mind these 2 queries because the rank is based on these 2 queries. And obviously of all the other features that are inferred. So these are the first 2 ranked houses for the GLRM and the deep learning without encoder. Let's remind what the user wants. So now, if we can see the matching between the query and the ranked house, for the GLRM, we can see that for the first house, the GLRM suggests, so the rankings for the query estimated with the GLRM suggests a house with only a bedroom. That is the only mismatch with what the user wants. But like a bedroom, if you want 4 or more bedroom, is not really like a good suggestion. For what concerns instead the deep learning without encoder, we have always the same amount of matching. But like the first ranked house has like more bathroom. So there is a mismatch always in bathroom, but we have like more bathroom. Do you prefer to like someone suggests to you like a house with more bathroom that you want or less bedroom? I think the second one, or at least I think that. And you have to keep in mind that this query, these features of the houses that like the user select are very particular. So there are not in our data set, our final data set, and so the engine should suggest something like that the user can appreciate. So now let's go to the interesting part. I will show you directly the application that we have done with FLASK. So we have this application that we can, this is the welcoming, the homepage. Then you can like go with the user profile, it shows your age, the citizenship, ethnicity, and so on. Then the core of the application. 1 second that I okay, is the house feature. So the first block are the main house feature of the house, something that you always select, number of total room, bathroom, bedroom, and so on. Then there are some other menus where you can choose some additional features, like air conditioning, if there are some steps, and so on. Also about something about costs, so about bills. And then about kitchen features, so if there is a fridge, if there is a sink, if there is a dishwasher, and obviously you can choose everything. I will close this. Okay, and in the end we have also some feature about the structure. So like you can choose the phone type, if there is electricity, gas, and so on. Now let's try to make a query. I don't want this. Okay. So we want 2 bathrooms, 3 bedrooms. We want a garage. We don't want a condominium. Then we can say that we want a separate dining room, but no more living room, for example. Then we can click the submit button here, or also here. And it's going to a page that is summarizing your selected query. So summarizing the features that you want. You can go back and change it if you want, and you still have here your choices that you can change, or you can confirm your query, and so the model is processing behind. Deep learning is inferring the missing value, and then is ranking the houses. This is the final data table that show the ranked house is focused only on the features that you have selected to see that there is really a match between what you have put and what the engine suggests you. If you want to see, I don't know, the first house, you can click on the index, and you can see all the features of the house to say, oh, yeah, I like it. No, I don't want this kind of feature. I don't know. And you can browse all over the table. And that's all. And then you can go back to your home. So, oh, sorry. Let's skip this. There was only if the internet was not going. OK. So to conclude, all this engine that we have implemented is all done in Python, from the backend to the front end, using that kind of library. So pandas, NumPy, H2O, FLASK, and scikit-learn. We have said that we have measured a better performance for deep learning with autoencoder that has a less error compared to the GLRM. And we have measured a better time performance for GLRM. Some extension that can be done are improvement of the algorithm based on the user profile. So we can use the user profile to cluster and to better infer the missing values. Another implement, last but not least, is the development of a faster approach to speed up the engine, since we have seen that it takes 40 seconds, that can be something for the user. And that's all. Thank you.
Thank you for your presentation. Now up to the questions. First question. I'm used to have the answer.
Okay. Thanks for the talk. I have a question about, maybe I missed something. So the first part is you have to infer every missing parameters of the query, right?
Yeah, practically, okay, you give some features of the houses, but in this case, we have 43 features, so it's not a user, it's selecting all the features.
Maybe 1, 2, 3, okay.
Yeah, normally you select bathroom, bedroom, garage, air conditioning, something like this. So first of all, you take these variables, and based on this variable and of the user preference of other users that have done some queries before, you infer all the other variables. So you infer the preference of this user. And after taking this query, you ranked all the database of the houses.
Yeah, my question comes to the first part. So you don't know which variables are going to be input by the user. You have 30 variables, so you can have any permutation or any combination of variables, and you want to predict any possible combination of missing variables, okay? So you have a predictive model for each possible combination, or?
The model is predicting all by himself, like both model, GLRM and deep learning, taking something that has missing values, is reconstructing all the missing values. Or is reconstructed, so in this kind we have in this type we have a query. So we have like, I don't know, 5 only features, and we have to infer all the other one. So we have a matrix of all the previous information. Thanks to that, we pass it to a model, and the model is reconstructing this metric, inputting itself the missing values. I don't know if I was clear.
Yes,
Dania, if you can
but
be clear.
my question was like, how do you give as input to the model, let's say you have 2 different queries. One time you have a query is a number of bathrooms, and then the next time you have number of rooms.
So
Then the same model can take, and then what do you give the model as missing values? So I miss a bit.
okay. So is it working? Yeah. Okay. So what we are doing is you have a history of a data set of all the previous user preferences. Okay. So now you will have a new user. The new user will enter, as I said, like we have a wide range of house features, as you saw. So nobody will start like filling all the information. So let's say you come and you entered like the number of bathroom, number of bedroom, and let's say you want fireplace. What the model is doing is taking this query, the new query that you have inputted, it's giving it back to the history that we have based on the previous users, and it will compute for you and impute for you the NAs based on the history that we have. Don't know if this is clear.
More or less.
Thank you. The last question?
Hi, thank you for the talk. I was wondering, actually you mentioned the GLRM and the deep learning model. Which one are you using in your production version?
Yes, sorry, I forgot to tell you. We use obviously the most, like the one that has the best performance, so the deep learning without encoder.
Okay, would it make sense to actually create an ensemble of the both models? Would that actually improve performance?
Actually, we have done this in the testing period. So we created some kind of a demo before this one. So this is the final version. It was computing the NA based on the number of missing value that we have. So the more missing value you have, as Chiara mentioned, you will like GRLM will perform similar to deep learning. So we were like giving the model to impute the NA with the GLRM because it was faster and it was basically the same performance. But the more we have like more missing value, let's say up to 90%, we will give the model deep learning. So we have done this before, but it was like just for a test. But then after like doing a lot of validation and tuning of the model, we found like deep learning was much better. And actually, as Chiara mentioned, that we are going with like in future with like there is another approach of doing the probabilistic. So you will have a pre-computed queries basically, so the model would be faster.
Okay, thank you. Can you also tell us about the scoring a little bit, because you basically just talked about the data imputation. How was the scoring implemented?
The scoring? Yeah, as Dania has told, the scoring formula for ranking was practically based on the scene. We have done the cosine similarity and weighting for the number of matching between the query and the houses, practically.
Could you have used another algorithm instead of these two? Yes. Do you think there's another algorithm that can better do the same scoring, like market basket analysis, a priori algorithms in that area?
So the market basket analysis, it's based on PCA, and as I mentioned, like our data set was heterogeneous data set, so we have different data type. And for this purpose, that's why we were using GLRM and deep learning, because they are dealing with different data type. Of course, like there is a wide range of algorithms that you can use, but in this particular case where you have like different data type, it was better to use these two models.
Any other? Yeah.
Hi.
Hey.
Sure.
What about accuracy, F1 score, and confusion metric about your model?
We have done like yeah, you go. Go.
Like that. Okay. No, you mean about the error for tuning the model? No, in the end, we have thought that since we are really inferring missing value, and in our use case we have, I can't understand.
Well, I was talking about testing and validating your model.
Yeah, actually, we have done the test. Let's go back. Yeah, so we done the test, and basically we were using. So the approach that we were using is, as I said, like since the data set that we have, it was heterogeneous, so we have ordinal variable, we have categorical variable. We need to have different, let's say, calculation for like calculating the missing variables, the mismatch. So what we were doing for ordinal variables that we have, we were just like to see, to compare the imputed query with the original query. And then to understand if, so let's say for binary variables with like yes or no, the Boolean variable, you will just see it if it's true or false. So just take the count of it. For the other variables, you will just take the distance, and then you will compute based on their like weighting of the mean of miss error between both of them.
Anybody else? No question? Okay.